In 2012, a few Missouri S&T students had a dream. It started when the Electric Formula SAE competition spread from Europe to the United States, and the first Electric Formula SAE car competition was held in Lincoln, Nebraska. Formula SAE cars are small, one-person race cars that have to perform all sorts of challenging maneuvers. Missouri S&T has had a gasoline-powered Formula SAE team for years, but an electric car brings with it a whole new set of challenges.
A lot of people think electric cars are slow, but like Duchess weighed 450 pounds and had a motor capable of about 100 horsepower, which is like really, really fast, like super bike fast. The chance to like work on something, design something like that, and actually drive it is super cool.
It is unlike anything you drive on the street. The mixture between the lightweight, it's a 500-pound car, the power, it's got roughly 136 horsepower unrestricted, and the tires that you get to drive on, it creates this experience that's like a pick-your-own roller coaster kind of thing. It can brake harder than anything I've ever driven or ridden in. It can turn harder. It can pull close to 1.5 Gs in a corner. It is hard to compare it to anything because it's so unlike anything I've ever ridden before.
A lot of the teams do some really great things here, but what kind of made it stand out was both it's an electric car, which I'm interested in, and also it's a race car.
And just driving a really fast electric car, kind of like a Tesla, it was really appealing to me.
But what really made me want to join the team itself is that we completely build a race car.
So initially I didn't really want to be on the electric team. I was trying to join the combustion team, but I couldn't find their shop. So I ended up here because this place is much easier to find. They're going to see that and be like, you idiot, it's right there.
What about the project? It's fast. That's why I wanted to get involved. It's because it's fast.
But how do you harness all that power, manage the traction issues in both straight-line acceleration and demanding slalom courses, maintain enough power to finish the race, while building a car that's safe, reasonably lightweight, and friendly for a student design team budget? Those are just a few of the many challenges facing this fledgling team.
So this was the first year we built a car in 1 year. Prior to this, we built Duchess, which was a 2-year build cycle because we were learning.
The first car, named Duchess by the team, was almost ready by race time. Without quite enough time to get the car fully finished, the team headed to Lincoln, Nebraska for the 2014 competition with hopes of getting the car ready before the racing started. S&T's race car could not pass the electrical tech inspection. They weren't alone, though. Of the 20 teams in the competition, only 3 of them passed the technical inspections and were allowed to drive. Still, after all of the points were totaled, Missouri S&T Formula Electric received 5th place, an excellent showing for their first competition. The next car, called Artemis, was built in 2016.
Fall 2015 semester was when a lot of the basic design started, and then designs were finalized in the fall 2015 and needed to be done by spring.
We decided to get a design that would be good for ease of manufacturing as well as good performance.
We had kind of like the plan, we had it mostly designed, but then once we actually got down to doing it, we found all these little problems everywhere, and we had to like fix those on the fly.
You know, there's a complex problem, and seeing the end result and knowing that you made that all yourself is pretty cool.
The design process starts with the power systems. For an electric car, the size and weight of the batteries is critical. S&T's battery is composed of 6 modules, each one with 11 cells. It weighs 161 pounds and puts out 8.6 kilowatt hours.
This year, I basically worked to redesign the battery box. What we started with was a composite structure that we were going to have, and that would contain all of the cells and everything for our battery. But one issue we had was rules. So we had to go from a composite to an aluminum, and that changed a lot of the dimensions on it. Composite is lighter weight, but it takes up more volume. And when you switch to aluminum, it's denser, so there's space that isn't taken up, and there's a bunch of gaps that you have to fill. So you have to redimension everything. With composites, it was kind of fitting together like a puzzle piece. So we also had to account that we're not going to key it into each other. A program that we have access to is SolidWorks, and we can completely model the whole battery box. You can run simulations on it to see the stresses that it can handle, you can run different models. You can kind of compare them together. When I got told that I was going to be doing the redesign from composite to aluminum, it didn't seem that hard, but I had never used the 3D software before, so I would go in every day and learn a little bit of new stuff as I was designing this.
Our battery is 66 lithium-ion cells. So a lithium-ion cell is the same thing that powers your cell phone, but the cells in this pack are much, much larger. So our battery pack could power your cell phone without recharging for about 3 years.
In the bottom, we have 6 different modules, and then the top that goes on top of it connects to that, and that has the majority of the control system. So it's not really just putting a battery down in a box. There's a lot more that goes into it.
So with lithium batteries, you have to monitor the voltage of each cell and you monitor the temperatures of each cell. So what that allows us to do is monitor essentially the health state of the car. So if one of those battery cells is at a lower voltage than all the other ones, then it might be that that cell is starting to fail or go bad, and so we might have to know to replace it. The other thing we can do is what's called balancing of those cells. So you want all your cells to be about the same voltage. And so we have a system in there that will actually go through and adjust the state of charge of individual cells. So you can burn off a little bit of energy to pull cells to put them all together. And that allows us to do things like charge the pack more completely and more evenly, and it also helps to improve the life of the battery pack. Our car is capable of 100 kilowatts. That's about 136 horsepower. The car weighs 500 pounds, so 136 horsepower may not sound like a lot in terms of a typical American car, but a typical American car will weigh much, much more than 500 pounds.
That's enough power to take the car from 0 to 60 in less than 3 seconds. Second in importance only to the power systems, the suspension is what helps keep the wheels firmly planted on the ground. The team uses a finite element analysis simulation in SolidWorks to make sure that each design is only as strong as it needs to be for that application. The pieces are manufactured out of solid blocks of metal and turned into the finished parts that we see on the car.
So the suspension is important to the car because it's everything that connects the wheels to the rest of the car and how those wheels move when you're doing things like accelerating or on the corners. It's important to get it right because there's a lot of ways you can really optimize getting the most traction and being able to accelerate as fast as possible, brake as hard as you can, and turn as hard as you can. We decided on a unequal parallel AA arm suspension, which is a Formula One style suspension that most of these teams are using. We validated the data on a program called Atoms and then designed all the parts in SolidWorks. And you can see how the suspension moves up and down under certain loading conditions. The uprights for the car, that's where the wheels and brakes are attached to the suspension points. It's a really cool looking design, and it's something that I think this team's really proud of.
Once the critical hardware components for the car are chosen, the frame can be designed. The frame also starts as a 3D model in SolidWorks. After the design work is completed, the actual building begins.
We bought the metal, and then we had to notch it by ourselves and then weld it together, and we had all students do that.
Well, I did spend 18 and a half hours straight in a shop once, because 18 and a half, because we were sending the frame off to get painted, and we didn't have all the flanges welded on yet. So me and Matt and Alex and Rob, we all just like cracked open the monsters that night. We got it all done, and we were pretty much dead in the morning, but it sent off to paint with most of the tabs on there.
One of the most interesting and challenging aspects of any electric car design is the software. When a driver pushes on the accelerator pedal, they naturally expect the car to move. The interesting part on an electric car is what happens in the background. The software takes that input and runs it through a massive number of checks before doing anything with it. It takes hundreds of hours writing code and testing it to make sure each module works as expected. As the team drives the car, graphs gather data from nearly every sensor, allowing them to modify the settings to further improve the car's performance. One of the best things about the software is that it's constantly improving. Now that the team has solid ground to start with, they'll be able to build it into something even more incredible.
There's a huge control system. Our car puts out, I think it was about 550 foot-pounds of torque, which is almost twice as much as the Mustang GT I used to have. It'll put out a lot of power, but all that power requires a lot of control. We have around 100,000 lines of code that were written by our own students.
The brain of the car is the main car controller. So that's a box with a couple of different circuit boards in it. So what that entails is everything from the control systems to monitoring safety systems, monitoring battery voltages and temperatures, looking at the pedal positions, and pulling that all together into a system that can work and feed the electric car. It also monitors all the safety systems, so things like if the batteries are getting too hot, you want to turn them off so we don't, say, light the car on fire. There's a couple other safety systems for things like if the throttle sticks or if the brakes stop working. It's monitoring all those systems to make sure that the car both works, but that it also is safe for the driver and for the people around the car.
It was a lot of making sure that those systems were in place, but that they also didn't cripple your ability to compete, because a lot of them will make the car shut down.
There's several different places that have their own code in the car. So the car controller has a few different processors in it. Each of those has anywhere from 50 to 100,000 lines of code. There's another circuit board that sits up near the pedals that measures the pedal positions. That has its own set of code as well. The battery monitoring system has its own as well, and so then all of those processors will talk to each other, and so they'll communicate and say, okay, I've got, battery temperatures is getting a little hot, we might need to turn the car down or turn it off if things are getting a little unsettled.
Okay, so I did the dash, which is a particularly fun project for me because it's kind of the human-car interface where you have some things that like the car wants to tell people, but it can't just say like, oh, I'm overheating right now. And even the sensors, that's still pretty low level. Oh, I'm putting out 2 volts right now. Like people don't want to know about that. They want to know like, is this too hot where I need to stop driving? When they're going super fast down the racetrack, they can still understand like, oh, I need to slow down a little bit or whatever it may need to say.
So I kind of floated around with a lot of groups this year. I do a lot of the manufacturing for the composites is probably where I put the most of the time. I helped with the frame. I spent some time doing that. We have the 3 body panels, the air intake and the exhaust fan, and we did everything in-house, and we are by no means professionals, but we did our best and we learned a lot from the process. We're always complimented at competition, especially by other new teams, about how professional our panels look. And we do get them professionally painted. Thank you, High Tech and Rolla. We do all of the composite layups, the molds ourselves. It sounds fun, but it's actually just hundreds, probably hundreds of hours of sanding, getting the molds smooth enough to lay up composite material on.
Part of the design of any good race car is the aerodynamics. One of the challenges with aero kits is the price in relation to what benefits they provide. Unlike the motor, controller, and battery cells, the car can run without an aero kit.
So this year I started out as the aerodynamics lead. I got the software necessary for us to do the design for aerodynamics to build wings. Partway through the year, due to time constraints, I sort of got moved to other projects, so I helped with manufacturing. I sort of helped make sure everything came together. I really like designing wings. I think it's really cool to see how it's so much different than so many other applications. Like a race car is just so incredibly different from like a plane. I was really disappointed, obviously, that we couldn't get the wings together. It really just came down to there wasn't enough time to make sure all the steps were taken to get to the final product.
Of course, everything about the Formula Electric team revolves around the finances. The team's budget depends almost entirely on the big 3 electrical components of the car: the motor controller, and the battery cells. They all combine to use up about half of the available funds. Moving forward, the quality of each car will depend in part on how many items can be used from previous years, allowing them to spend those budget dollars on additional improvements.
So the way our team is funded, we get donations and sponsorships from companies. The school funds us a reasonable amount. So you have to go in front of the board, S&T, the AMA board. They know what you're talking about. Don't lie to them. They'll call you out on it. And you have to give your presentation and justify why you deserve their money, essentially. Everything else is funded from local companies, individuals. We get a lot of in-kind donations from companies that have products that we use. So as business manager, my job is to find sponsors and to do a lot of the PR presentations for the team. I go to a lot of PR events. I travel for the team a lot, just around locally, to make sure people are aware of what we're doing. I also manage, or do my best to manage, the money. And when you have a large group of engineers trying to do their own pet projects to make the car run, it becomes really difficult to keep track of all the money. It's difficult to tell an engineer who's trying to do the right thing and do everything the correct way that we can't afford it, and to do it the slightly less right way. Most of the time, most people are pretty aware of our financial situation, the fact that we are funded by donors and by sponsors. So most of them do their best to reach a compromise between cost and effectiveness. It's hard to cost save and be competitive. So not to say we buy the most expensive things possible, but there's some products that you need to be competitive. So there are some certain purchases that have to be made and that you can't really get around. So in order to cost save, you do your best elsewhere, and a lot of that's reusing parts if they're safe to be reused, being frugal with your design process, trying not to break things when you get them. A lot of testing should be done, but because of our financial situation, we do our best to do FEAs and SolidWorks and stuff to validate our designs instead of doing real-world tests that would break what we make and then making it again.
The team has exactly 1 year between competitions. In the future, as the team builds on the current knowledge base, the designing and building phases will become progressively shorter and the testing phases will become longer.
So we are engineering students. We don't really have a lot of experience when we come in here. We're here to build that experience.
So we all have tests and homework and that type of thing, so it's hard to put in the amount of time really needed.
It was really hard to balance finding enough time to do well in school while still putting in all the effort necessary to getting the car done.
Like on average, some people put in like 30 hours a week is a pretty solid amount. You're doing a lot of work. I mean, between that and school, that's all your time. Some people who just spend ridiculous amounts of time, those are the people that make the car get done in times.
I was doing these one parts so much that I actually had a nightmare that I set it up wrong and was going to break a tool that night. Like I was just like, oh, don't do that. I'm all right, I'm in bed, so it's cool.
It's one of the things you do that you learn so much more than you ever would in a classroom.
It's a lot of learning and building and researching and talking to people out in industry, researching things, finding published papers, ways other teams have done things.
The biggest thing I've learned is that nothing will go right the first time. You always have to plan for that.
Having hands-on experience has just tons of lessons every day. There's some design experience I've gained from actually like building the parts where I know like what to avoid. Like you have to be able to put a wrench on a screw. You have to be able to get at both sides so you can tighten it up, you know? If you're just designing things, it's way too easy to make those mistakes if you've never actually like been with the real parts.
In the real world, engineering is almost entirely working with people to solve problems.
I can't do anything here by myself because I've never done a whole lot of it before. I was really interested in cars, but I've never built a race car.
It's a lot of, for lack of a better term, trial by fire. You get thrown in these situations that, maybe you don't know how to do it, but there are guys on the team that do know.
I'm a pretty quiet person. I tend to keep to myself a bit, but being on this team, you have to put yourself out there a bit. You have to talk to people. That's the most important thing, because there's a lot of times where we just couldn't get things done, and it was because one person was waiting on another person, but that person was waiting on the first person, and so neither person was getting anything done because they didn't know the other person was waiting on them.
We always have some very knowledgeable people, but because of how knowledgeable they are, they're always busy. And it makes it hard to teach new people who can then become knowledgeable, and it's just this perpetual loop of trying to transfer knowledge.
Part of it was that we had seniors graduate in December, and so they didn't really continue working, but not all of their designs were finished. So it was left to other people still on the team, still around in town to sort of pick up where they left off.
By competition, they still had not been able to fully test the car to its limits, and therefore were not able to push it as hard as they would have liked.
We started out and we had a grand plan of what we were going to end up doing, but as things rolled on, a lot of stuff got pushed back.
We were sort of struggling to get all the work done in the last few months before competition.
We finished the car about 2 weeks before the competition started, and we would have liked a lot more time to test it and drive it and stuff.
But our car ended up working out pretty well.
This year we actually got through competition, we got through tech inspections, we were able to run and race at competition.
In 2016, S&T again finished in 5th place.
I think it was really worth it. I really like being on this team, and I think we have a lot of great guys on this team, and it's a race car. It's pretty cool.